So my talk is on Trustworthy AI based on Analytical-Model-Informed Machine Learning. And also I will open some open question about AI scientist tools, which are now a new extension of Analytical-Model-Informed to more complex tools for scientists, but also for engineers. Okay, so my talk, I will start with physics-informed machine learning for engineering on numerical simulation, just to show you that this kind of technique is more and more used, especially in the industry. Then I will introduce you what we call analytical-model-informed machine learning in Thales. So we have two families, TINN for geometry-informed neural network and PIN for physics-informed neural network. So the first tool is GIN is for capturing the symmetries of your problem and reducing the dimensionality, and PIN is also to reduce the need of data by capturing some constraint on physical law. But physics-informed neural network is progressing very fast. Now we have advanced physics-informed neural network which are developed like HNN for Hamiltonian-Informed Neural Network that try to learn the Hamiltonian or Hamiltonian field, and a more recent one with the Symplectic Foliation-Informed Neural Network. And then I will conclude with toward the AI scientist tool, which are new advanced tool try to help the engineers or the scientists to do their job. And I will make references to European action. So we have two European action, COST Calista on MSCA, which is called Caligula. And we are in process to propose a CaliQuantum project. Okay, so physics-informed machine learning for engineering on numerical simulation. So our engineers are using more and more intensive numerical simulation for the optimization of the design of our equipment and for the different engineering phase. So it's very important now for industry to optimize the design of the equipment, and so to use these new high-power computing resources to transform new degree of freedom in new improvement in the performances of our equipment. So here I give you some conferences or seminars that you could find. So recently in France, for example, you have a simulation on AI. So it's addressed physics-informed neural network in the car industry, developed by Technocentre Renault Group. But also Dassault Aviation is working on this kind of technique for BizJet predictive maintenance. On two examples of seminar in US and UK. So at Caltech, you have the physics-informed learning and computation seminar, and at in UK at the Alan Turing Institute, physics-informed machine learning meets engineering. So you could find some the video on the Alan Turing Institute website. Recently in France, we have been invited by KNDS and Saint-Cyr-Coët-Quidor, which are working for the French Army, on a seminar on AI on simulation. So AI is also more and more used for simulation. And so we have to improve the trustworthiness of this AI for this simulation, because it could have an impact on security of the system and also the training performances. On the French side, we have also many activities at the French CNRS has recently launched physics-aware machine learning group. You have here the website, and last week they have organized a workshop day on physics-informed machine learning on large model. And also this week there is EDF EA EDF in Summer School on Physics-Informed Neural Network. The title is Solving Partial Differential Equation in Field Physics Faster with Physics-Informed Machine Learning. And also in France, in many clusters of AI, here you have the example of ANITI in Toulouse. They have an integrated project which is called PhySim AI that address also physical simulation. But also the digital actors like NVIDIA also are positioning their assets on this topic and try to use their high intensity resources of computing for physics machine learning, and they have developed a Physics Nemo platform. Here you have a slide of their technology. Among the technology of physics-informed neural network, in Thales we put that in what we call analytical-model informed machine learning. And we differentiate in two categories, geometry-informed neural network and physics-informed neural network. So it is a slide I take to my colleague Juliette Mathioli on what we define in Thales in terms of hybrid AI, where we have model-informed neural network, especially the coupling geometry and physics, but you could hybrid AI with different model. It could be also knowledge representation, natural language processing, but here I will focus on model-informed neural network and try to constrain neural networks with physics constraint and geometric constraint. So it's a more digital approach. So this is classical to explain physics-informed neural network. So on the right, you have a lot of data on no theory. Classically, GAFAM, they like to be able to explore medicine without learning medicine, to make electromagnetic simulation without knowing anything on Maxwell equation, or fluid mechanical model without knowing nothing at Navier-Stokes equation. So you have some company developing, for example, a weather forecast with our ANI model, but only by learning on data. On the left side, you have we have like in the military domain, we have not no data, but very little data on a lot of theory. So we have developed many models during a long period. And these models are accurate, but in some type not accurate enough, and try to use them as a maximum of their capacity. And physics-informed is in the middle to use the best of the data learning on the best of the theory. So we define two categories. The first one on the left is geometry-informed neural network. So sometimes neural networks, classical neural networks, could have lack of robustness with respect to geometric transformation. When I learn to my children to recognize a cat, I just have to present them 2 or 3 images of cat, and they were able to recognize a cat. Why? Because they use the symmetry and invariances, the geometric invariances of the object. On classical neural network, we are only convolutional neural network are only equivalent to translation and not to other geometric transformation like rotation or coupling, rotation, and translation. But we could add also scale invariance, contrast invariance, which is very important for Thales application. So one solution is to use data augmentation. But when you use data augmentation, you have more data, and so it means bigger neural network, and so resource consumption, and also it's not very well adapted for embedding system, which is the core business of my company, to embed AI on platform. So solution will be geometry-informed algorithm, try to capture this geometric constraint and to ensure mathematically that you are robust to this transformation. So it's also very important for Trustworthy AI because you can prove mathematically that you are robust to this transformation. On the right side, we have a physics-informed neural network. So sometimes, if we compare classical methods, so deep learning, they are requiring a large amount of training data. And digital simulation requires a perfect knowledge of the underlying physics. So sometimes we have very good analytical model. But we are not able to modelize all the phenomena. So you could have some phenomena of saturation, some phenomena of coupling, some dissipation phenomena, which is very difficult to write analytically. But we have a first good approximation by the model, and we'll try to correct the model with learning on data. So what about GIN? So geometry-informed neural network. So one very illustrative and simple example. So on the left, you have the classical neural network. So classical neural networks, they are only equivalent to translation. This is their main properties on the success of a convolutional neural network. Is that this expression of convolution is equivalent to the translation. But it's not equivalent to a rotation and not equivalent to roto-translation. So if you want to make your neural network able to recognize your object in different rotation and translation, you have to use data augmentation. So you take your database and you augment your data by applying the roto-translation, so translation and rotation to your database. So you have a very big database that will induce that you should have also a very big neural networks to have good performance on this big database. On the right, the mathematicians have developed during the last century extension of convolution on, so this is a complex formula, but just what mathematicians call convolution on Lie group. So you consider Lie group, it is matrices that applies a symmetry on your data, and you can define a convolution on this Lie group. So here you have three kinds of Lie group. You have the translation, you have the rotation in the middle, which is called the Lie group SO2, and you have the rotation and translation on the right, which is called a special Euclidean group SO2. And as you can define convolution on Lie group, you will be able to define by design some neural network that will be robust to this transformation. Okay, so it's very important for Trustworthy AI because on the left you have to prove to your authorities that your data set is representative to all the geometric translation transformation that could be applied to your model. And on the right, you can prove mathematically that you are robust to this transformation. Obviously, you can complexify, you can add scale invariants or also contrast invariants for this application. So in Thales, we have studied this kind of neural networks and also extended to fisheyes camera. So fisheyes camera is used in many applications now for video surveillance, for instance. And so you have a 1/2 sphere. And the problem is when you try to learn some object and recognize some object with a fisheye camera, as you have a very nonlinear transformation of your images, you have to be sure that you have learned objects in the different position in the lens of the fisheye camera. Otherwise, you will not be able to recognize it. So the main idea at Thales is that we have, but the problem we have no symmetries because we are on a half sphere. So the idea was to project this half sphere on the unit disk. On the unit disk, you have a Lie group that act, which is called SU11, special unitary group. And then we can apply the theory of equivariant neural network and make robust the fisheye camera to any geometric transformation. So if you have an object on your camera, like a drone, you can recognize it if it has a zenithal position or at low elevation of the camera. You can find, for example, for Earth observation, you can consider the Earth on all the SO3, so rotation equivariance of your data for climate analysis, for instance. And so you can also build SO3 equivariant layers. In more complex representation of data, we could have not only on images, but in Thales we have applied also on radar data. So it's more complex, but we are decomposing the signal in complex representation in polydisk of Poincaré, where you have data, the SU11 equivariant. So we will explore a more complex model in the European Marie Curie action that will be launched, that is called Kali Quantum Project, where we will extend to a more complex space of covariance matrices, but I have no time to explain. The second topic, physics-informed neural network. So, as we said previously, so physics-informed neural network, they can embed the knowledge of any physical law. And this physical law govern a given data set in the learning process. And then this can be described by a partial differential equation. This physical model, in fact, are embedded in the learning process and could be considered as a regularization constraint in the loss function. And so the prior knowledge that we are using are the general physics law that act in the training of the neural network. So this regularization property will be used to have a more robust neural networks, and also you will need less data to learn your model. But you can also use another property of neural networks for simulation, which is called a surrogate model or model order reduction. So classically, in the first case, you have no model, okay? So like for the GAFA, you have no model, so you use only real data, and you use learning to have to define a surrogate model. The second case, you have an accurate and validated analytical model, but it don't run in real time. Okay, so you have a very good numerical chain that makes the simulation, but it cannot run in real time. So the idea is to generate simulated data with your analytical model to learn a neural network. On this neural network will be a surrogate model, a model order reduction, and it could be processed in few milliseconds compared to your hard code that is not able to be processed in real time. For example, if you take Airbus, the braking system of Airbus is a surrogate model. They have some code to defining the strategy of braking of the aircraft, but they use a surrogate model for the braking. On physics-informed neural network, it's different. You have some real data, but not so much. You have an analytical model, but you have, when you compare the real data of the input or output of your system, there is some error. And then what you are learning is the error of the analytical model. And so you will put a patch that will correct your analytical model. So classically, in analytical model, we use the data for data simulation for the calibration of the model. But with physics-informed neural network, we are learning what we unknown of the model, what is not captured by the analytical equation. So it could be dissipation, it could be nonlinear phenomena, it could be saturation, it could be coupling between elements. And you can use both also, because you can use the neural network to speed up your simulation because it runs in real time, and you could use the physics-informed neural network to capture the ignorance model. And so you have a better model, more accurate, and running faster. So I will give you some example of use case of physics-informed machine learning. So this first one is the tool WAT, developed by Thales. For WAT means Thales Thermal Analysis Workbench for Thermal Engineers, which has been developed by Thales 6, TSN. And so you will use the equation, the thermal equation to constrain your system, and you will penalize your loss term related to the data by a term related to your partial differential equation. And it's mainly used to capture and predict thermal behavior of your electronic card, for instance, on our system. Yes, and they have mixed this physics-informed neural network is very interesting because it's a mix between physics-informed neural network and convolutional neural network. So we call it physics-informed convolutional neural network. This example has been developed by Cortex Lab in France. So it's how to, with Thales LAS, non-linear system, for radar application, so electromagnetic simulation, where we have to modelize on a very wideband response an element of an antenna. And then we will use the Maxwell equation to constrain the physics-informed model, but we have also to constrain with respect to the source and also the boundary constraint of the system. So this project is continuing also with the Astrid project, where we will explore other electromagnetic model. Another one is for drone, where you have now a flight mechanic model. So we know very well the equation of flight mechanics and how to use it here to try to detect as soon as possible a failure if you have a failure on your drone, you have to detect as soon as possible for air traffic management of the drone. And so we can modelize what is a normal flight mechanic on some anomaly of the flight mechanic. And also we are collaborating with CNRS in a project which is called Descartes with Francisco Chinesta in a project in the CNRS at CREATE in Singapore, where we try to develop an hybrid digital twin able to compute turbulences in real time. So here you have the town of Singapore with a different building, and when you have wind, the building will generate turbulences, and these turbulences are very dangerous for a flying drone, and we should be able to compute in real time this no-flying zone. And it was not able with digital code of flight mechanic simulation, fluid mechanic simulation, sorry. And the object is to use it to optimize the trajectory of drone in an urban area. And another topic is GNSS positioning. So we have developed with Thales 6 on CNES system some code which is able to compute the accuracy of positioning according to the satellite constellation, especially in urban environments. So if you are familiar with if you try to use a Google Map in urban environment as a pedestrian, you will see that you will have a very difficulty to make your localization. And so it's very important for drone to be able to assess in real time the accuracy of their geolocalization according to the satellites, of course, due to masking, but you have very complex phenomena as diffraction of the electromagnetic wave along the corner of the building, and also you have the multipath of the electromagnetic wave of the GPS signal. So and you have to capture that, and it's very complex to put this complex phenomena as a multipath and diffraction in equation to run it in real time. Okay, so it was what I call first generation of physics-informed neural network, but now we have more and more complex physics-informed or analytical model-informed machine learning. So I have identified two kind of family. The first one, what I call symplectic-informed neural network, and the second one, language model-informed, which will be related to AI scientist tool. So on the left is a symplectic informed neural network. So what does it mean? Symplectic geometry. In fact, many phenomena could be modelized by Hamiltonian system. In Hamiltonian system, you have two ingredients. The first one is a Poisson bracket, and the second one is Hamiltonian. So if you are familiar with mechanics, you can describe your Hamiltonian system by a function h and by this derivative on your position on the on p, which is the mass by the velocity. But you can also rewrite in very synthetical way the evolution of the dynamical system by this equation with what we call a Poisson bracket. On what is the main advantage of Poisson bracket compared to classical partial differential equation? The Poisson bracket will capture the symmetry of your problem, and the Poisson bracket will capture the invariant of your problem. So you could have different invariants in physics. Classically you have for time translation you have the energy invariant, but you could have other invariants like moment map, angular moment map invariants. I will show you some example. We also remark the arrival of large language model also for this kind of numerical simulation or model. I make reference to the recent work of Amaury Hayat from École des Ponts in France. So the main idea is that you can code an equation like a series of characters, and you can apply LLM model on this time series of characters that will describe your equation. And so you can learn some equation. So the problem of Amaury Hayat is a problem of command and control, where he has to build a function to prove that his system is stable. So other recent example of this kind of application. So on the left, you have a physics-informed based on Hamiltonian neural network. So it's the purpose of learning trajectory of Hamiltonian system for n-body system. So from the more simple one to pendulum to a three-body system. You know that a three-body system, it could be very complex, or not yet captured by physicists and mechanists. On the right, you have a pin based on LLM. So it's a paper on about in-context symbolic regression. So it is used for function discovery by the large leveraging large language model. So one important topic, what is very important in physics, is the notion of equivariance that should not be compared to invariance. So you have a white paper that I like a lot. Is this paper written by Princeton, Yale, MIT, Berkeley, Chicago, Google, on different physics lab in US, symmetry group equivariance architecture for physics. So this equivariance that you will capture will be very useful for learning by capturing the symmetry group. You have an impact on the model size and complexity because if you capture the symmetry, you will reduce the size and the dimension of your problem, and so its complexity. It has impact on interpretability because you will constrain your system to a physical law and symmetry and equivariance of your problem. You will win also in sample efficiency because you will reduce the number of data you need to learn to apply learning on your physical phenomena. Generalizability also, it will be more robust. It's a more compact neural network, and so it's like a polynomial. When you have a polynomial, if you have a polynomial of low degree, you have less oscillation, and so you can extrapolate outside the data set you have used for learning and maintain some performances. And also faithlessness to physical law, obviously, because you are based on the physical law. So you have many advantages to capturing this equivariance. So many problems have been modeled with Poisson bracket. So it's an extract from a paper from François Gebelmaz that we are collaborating with in Thales. We have developed a Lie Poisson neural network, and here I give a table of different problems of rigid body, heavy top, underwater vehicle, plasma, fluids, geodesical fluid dynamics, complex and pneumatic fluids, molecular dynamics, fluid structures, quantum classical dynamics that could be modelized by Poisson bracket. So first approach of this new generation physics-informed neural network is to discover the Hamiltonian system. Okay, so you have some most well-known are Hamiltonian neural network, HNN. So the idea is to approximate the Hamiltonian function by fitting evolution of a specific data sequence through this canonical Hamiltonian equation. But you could also include adaptive learning for systems which are chaotic systems. You have also considered not the Hamiltonian by the dual function, which is the Lagrangian. So you will have the Lagrangian neural network. You could also try to learn vector field for in case that you have a non-canonical Poisson bracket. And also you can learn the Hamiltonian vector field. The second approach is to learning the structure preserving flow of Hamiltonian system, which are canonical Hamiltonian system. And in this case, you could have some learning gradient or learning scheme which is related to symplectic integrator. So you have a notion of symplectic recurrent neural network, non-separable symplectic neural network, SympNet, generating function neural network, and EONNet that could learn Poincaré maps of Hamiltonian system on preserving the symplectic structures. So you have different new Hamiltonian neural network which are based on symplectic integrator. So why symplectic integrator are very more efficient? Because when you are using only Hamiltonian, you will preserve some invariant, but you will not capture simultaneously the symmetry of your problem. And the next one is, in some case, you have the case of non-canonical Hamiltonian system, and then you have the notion of Poisson neural network. And what is important in this case is to preserve Casimirs. So I will explain you in one example what at the end what Casimir means in physics. But Casimir will capture some invariants of your problem. So the Casimir function are invariant invariant function on relative to the Poisson bracket on what we call also the coadjoint orbit, which are generated by the symmetry, which are related to foliation, what we know call foliation. So in Thales, we are exploring this approach. Especially, we have first studies with François Gebalmaz, which was previously at Paris at CNRS, but now is also working at NTU in Singapore, and we try to apply that for the use case of quadrupter helicopter dynamical equation with a Lie-Poisson system. So the neural network is called LPNet for Lie-Poisson neural network for capturing the flight mechanic of the system by modeling by Poisson bracket. And we have some discussion with another lab in Czech Republic, in Prague, University of Prague, using HNN. And with the idea is to extend this model to capture also dissipative phenomena. So this is one example of Lie-Poisson neural network. So I will not give the detail of the equation, but this kind of system here, like a drone or satellite, could be described by a Poisson bracket, Lie-Poisson bracket, and then you can reduce this Lie-Poisson bracket equation by this Euler-Poincaré equation that captures the symmetry and the invariant of your problem. But there is one problem with the Poisson bracket that on symplectic integrator, you can only modelize non-dissipative phenomena. Okay, we will see why, but when you use Poisson bracket or Hamiltonian equation, so Hamiltonian neural network, this is a conservative equation, and so you cannot modelize dissipative phenomena. And in physics, almost all physical phenomena are dissipative, but classically we make the assumption that we will neglect the dissipative part. And so during the 80s in US for plasma physics, they have developed what is called metriplectic integrator that exactly use Poisson bracket, but you have another dynamics, which is another bracket, but it is a metric flow bracket that will drive the dynamic of the dissipation. And we will see that you will preserve the first law of thermodynamics, the preservation of energy, so preservation, quantitative preservation of the energy, on the second principle of Sadi-Carnot, which is the entropy production or the qualitative degradation of the energy when you transform, for instance, the mechanical energy to the heat energy. So I will not give the equation, but I just try to give you what is behind this equation of metriplectic. So metriplectic means metric and symplectic, because you have two terms, one which is metric flow and which symplectic one. And in fact, you can describe this dynamics by two functions. H will be the energy, and S will be the entropy. And in fact, the dynamic of the system is given by two foliations. So perhaps you are not familiar with the mathematical definition of foliation, but I'm sure that you like some very good dessert, which are some very good foliation. Well, so in French we say millefeuille, so I don't know what we say in English. So you have a very basic notion of foliation. So you have different leaves, and you have one foliation that will be the level set of entropy, and so constant entropy. Each leaf is the constant entropy, and transversely, so transverse in the sense of symplectic transversality, you have another foliation, which is the Riemannian foliation, and which are the level set of energy. Okay, so it's very easy to understand dissipative phenomena. You have two foliations which are transverse to each other. So one with Poisson bracket, you are moving on the level set of entropy. So at constant entropy, you are not dissipative. And with the metric flow bracket, you are moving transversally on the level set of energy. And you are moving from one leaf to another leaf of entropy, so you will increase the entropy, and so you will be dissipative. And so the mathematical definition is to say that S, the entropy, is the Casimir function of the Poisson bracket, and H, the energy, is the Casimir function of the metric flow bracket. So in neural network, we will capture these two constraints by these penalty factors that will be added to the compliance to the dataset factors, and you have a composing penalty to capture the dissipation phenomena. So I will skip that. Just to make the link to classical thermodynamics, you should be familiar with the Sadi-Carnot cycle. So classically, we represent Sadi-Carnot cycle with respect to volume and pressure, but you can represent it also indexed by entropy and temperature. And on this double symplectic transverse leaf, you can represent this cycle on this figure. Okay, I skip that. So it's used we are using many mathematical tools to capture all this symmetry. So Lie group and Lie algebra to capture the symmetry. So it's called representation theory. Symplectic geometry and Poisson geometry, which are describing the integrator on the dynamic of the system. The theory of integrable system, because in some cases, system are related to a complete integrable system. On foliation theory, which is a very important idea that you are not looking at one solution of your equation, but you are looking at all the solution of your equation that generate this foliation. So information geometry are also behind this model. Metriplectic flow I introduced, and obviously you can introduce in all that in calculus of variation. Also, symplectic geometry is a very long story, so I have no time to explain, but so we are continuing to explore all their advantage. I will skip that also. I have no time. So in Thales, we are exploring this metriplectic flow that use a model which is called Souriau Lie group thermodynamic, which is an extension of machine learning on Lie group, describing non-dissipative phenomena, on metriplectic flow for dissipative phenomena. Just make one remark. So it's just 2 years ago that Baptiste Coquino has proved that from École Normale Supérieure that the metriplectic flow is compliant with Onzinger relation, which is a classical out of equilibrium relation for thermodynamic. And you have the theory of foliation that has been introduced by Ereshman and Reb during the 60s. Just to conclude, to make you what is the link between first and second principle of thermodynamic. In fact, when you have this bracket dynamic, F is the Hamiltonian, is the energy plus the entropy. So if you want to have the first principle, you consider the derivative of the energy with respect of time, and it should be equal to 0. And to be equal to 0, so the first term is equal to 0 by symmetry, and these two terms should be equal to 0, meaning that the entropy should be a Casimir function of the Poisson bracket and energy of the metric flow bracket. On the second principle, so you consider the evolution of the entropy, and you look at the different term, and you have only one which is not equal to 0, and it is the metric bracket of SS, and it should be a positive definite. So it means that you have a positive semi-definite bracket. Okay. So as I explained for neural networks, so if you are interested at EPFL, they are using another term. They call it they call it general equation for non-equilibrium reversible irreversible coupling. So it's called generic for this abbreviation. And you can rewrite the metriplectic equation with the two constraints. And so you have matricely, you have two matrices, L, which is a Poisson antisymmetric matrix describing the reversible Hamiltonian dynamics, and M, which will be the friction symmetric positive semi-definite matrices that describe the irreversible behavior. And then you can build a penalty function with one term related to the data and one term related to the two metriplectic flow constraints. So to conclude, and it will be my last slide, so we have seen that it is very useful for engineers and also for scientists to modelize physics and to capture what they don't know in physics because they are not able to write analytically all the phenomena. There is no emerging tool, which are called AI scientist tool. So I make reference to a very recent paper of Nina Miolan, which was a PhD student of Xavier Pennec at INRIA, but now she's in Barbara in Berkeley, in California. And she has a provided a paper this month, the fifth area of science, artificial scientific intelligence area. So his explanation is very interesting. So first area of empirical science, using a report observation, with followed by a second area of theoretical science, where we will put in equation the physics, and followed by, during the 50, by the third area of computational science, where we will run simulation, followed by, during the 2000, by area data-driven science, with learn from data. And now we enter in an area of artificial scientific intelligence, where we will mix AI to make autonomous discovery of physical phenomena, or model to describe this phenomena. So you have different AI scientific tools. I will not give all the details. So you have MIT, you have AI Feynman, using a symbolic regression method for physics-inspired techniques. You have IBM with AI Descartes and AI Hilbert, also combining different technology of AI. Also Oxford University with LLM-based pipeline to generate new knowledge. And more recently, AI co-scientists by Google, also using a multi-agent system based on Gemini 2 to collaborate and help scientists in different phases of recovery. And also I make reference to Sakana AI, which method to automatically merge the knowledge of multiple LLM. So they try to use LLM to discover a new objective function for tuning other LLM. Very interesting approach. To conclude, so these work are addressed into European action. So Caligula, which is a cost action funded by European Union, on MSCA Caligula. So you have some website if you are interested. We have a different workshop. On the last one, sponsored by Calista, was at École des Mines, Mines Paris Tech, in Paris, where we have organized a workshop on geometry-informed machine learning, and I was in charge of a day on physics-informed and thermodynamics-informed machine learning. So if you are interested, you have here the website and also the link to the YouTube channel of the video. And if you are interested by foliation, symplectic foliation model for thermodynamic phenomena, I have written a paper recently on this topic. And we will address this topic in a conference which is called Geometric Science of Information, that we have launched for more than 12 years now. And this is the 7th edition, and we are address geometry-informed and physics-informed neural networks. And we could see also that metriplectic equation are also very fundamental, and I have launched a special issue to capture all the phenomena that we could modelize with the metriplectic system. So metriplectic is more for classical system, but you can extend for quantum system. So especially the Lindblad equation, which is used in quantum thermodynamics, especially for quantum feedback for qubit regulation by, for instance, Pierre Rouchon at École des Mines, is a linear approximation of metriplectic equation. So you can also capture and modelize and learn quantum physical phenomena with metriplectic and dissipative equation. Okay, so I have put some references, but I'm open to answer your question.
Thank you a lot, Frédéric, for this very, very rich presentation. I see people uploading. Yeah, a lot of material in your presentation. I was expecting a few equations, and I was not disappointed.
Not so much.
Not that much. Not that much. So there was initial question by Juan Carlos. Puentes, do you still want to ask your question? Maybe not. Maybe not. So let's. Yes.
Juan. I have one, but I'm. It's not Juan Carlos. It's Juan David, right? I don't know if it's the one that I put in the chat.
Okay.
Yeah.
Juan David. Wait a minute. Yeah, there's Juan Carlos and Juan David. Okay. So if you allow me, okay. So then please go on Juan David.
Okay, so the first one, I understood you already did some YOLO X implementations, Frédéric. So the first question is already inner source this one, or can we reuse it? And also, if apart the rotation, which are the other geometric transformations you use?
Yes, so we have YOLO, which has been developed by Cortex Lab in France. So you can contact Theodora Petrizer to have access to this to their neural network. So it's mainly for rotation. We have just launched a PhD with Santiago Velasco from École des Mines de Paris. So in fact, perhaps you are aware of Prairie PSL, which is a new second phase of cluster of AI in Paris downtown. At Mines Paris Tech, they will work on geometry-informed model. And so we have launched, Cortex Lab has launched with Santiago Velasco a PhD where we try to capture scale invariants and also contrast invariants also. Okay, so it could be interesting in many applications how to capture in the neural network these invariants. Also because it's easy to prove. It's always the same things. You can do the same things by data augmentation. Well, not exactly the same thing because there is some papers that proves that we could be intrinsically better with this kind of numerical chain where we capture by design these invariances. So there is some paper. There is one paper from Pierre-Yves Lagrave previously from Thales and also some academic labs proving that intrinsically we can be better than data augmentation. Because some people say, oh, no, okay, we can improve, we can make a lot of data augmentation and we'll asymptotically recover equivariant neural network. But now there is some paper proving that we are better by design on intrinsically in terms of performances.
Yeah, okay. So the ratio part is not done. So by the time being, it's only done on rotation, right? If I understood.
Yes. Yeah. So why is less popular than other neural network? Because the numerical chain are less optimized. So you have less GitHub with available equivariant neural network. Also, their coding on processor is more complex on GPU. So it's why it's less popular. But for example, quantum computers are very well adapted for quantum group convolution. So for group convolution, when you replace translation convolution by group convolution, some labs in MIT, for example, are addressing the quantum group convolution processing and try to see if quantum computer could speed up this process. So it's mainly the main reason why these neural networks are less popular than the classical one is that you cannot find optimal chain on code on GPU to speed up on yes. So it's more in labs. We have many labs in Europe looking at that. So in France, but so you have Max Welling on Eric Baker in Netherlands, Remco Dwight also on geometric. But you have Bronstein also in Imperial College of London. So you have many community in Europe, in UK, Netherlands, France, working on this topic.
And just two more. So regarding the things that you already did, did you already implement things like control of the position between objects in the scene, or relative position between objects?
Relative position.
Yeah, for example, imagine that one object should be on top of the other one, let's say, and then for sure with the delta, depending on the way you take the picture, etc. But the idea is to manage the relative position between objects. Did you?
Okay, no,
Can you easily?
No, I'm not sure. I'm not sure if this is a use case of this technology. But,
okay. 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 Thank you. Yeah, the last one is if you have an intranet page where we can take a look to the experiments that has been done, and so then we can take a look on more detail.
Yes, for Thermodynamics-Informed Neural Network, we are collaborating with Elias Cueto. So Elias Cueto is involved in the Descartes program in Singapore. So you have many experiments of generic on metriplectic flow for thermodynamic neural network.
Just to be fair, there's a Pierre Constantin waiting to ask for a question.
Yes. Hello, Frédéric. Thank you very much. You made my day. Just a very short question. Is there a way to somehow embed the knowledge that you can have, for example, from a pin into the structure of the network, other than between brackets, just on the loss or regulation layer? Somehow, more strictly embedding the knowledge at this point in time. Is it really the state of the art is to put it like described in the regulation layer?
Yes. In the technology of physics-informed, you have new branch where try to code in the structure of the neural network the constraint. So yes. I'm not following all the development because you have many, but I know that it exists. And I have not made reference also to Adagos, which is a spin-off of Institut Mathématique de Toulouse. They are using another technique which is also useful, which is a topological gradient, where they start with a very small neural network and they increase the complexity of the neural network by topological gradient until to reach their performances. So they have a very small neural network and with better performance than pruning, because pruning of neural network is you can reduce by 10% or 20 maximum. And here they have a very small neural network, and when you have a very small neural network, it's more robust to extrapolate outside your data set of learning, and it's very used in industry. They are working for Renault, for car industry. And in Thales, we are using their technology for electromagnetic simulation, for instance. So here there is no physical model, but more the idea to have a small neural network.
Okay, so because there's also Rasha Frigi waiting for a question, and that will be the last one because we are already five minutes after the finish time. Rasha?
Okay. Yeah. Hello, everyone. Thank you so much. So I have a question regarding the physics-informed neural networks. Actually, Frédéric, I want to know, based on your experience, what types of physical phenomena or systems that are particularly well suited for these type of neural networks, and if there are specific also domain where maybe they tend to have limitations or maybe struggle, underperform, or maybe outperform.
No, I think there is no limitation. You can apply in, I think, all domain where you have analytical model. So the limitation could be, for example, a chaotic system. when you have not also a complete integrable system, so especially when, yes, a chaotic system. But dissipation, we have seen that we can address also this phenomena, which was a few years ago, it was a challenge. But now we have a way to model dissipation. In quantum physics, I think that in quantum physics, it could disrupt some domain because especially in quantum simulation, quantum physics simulation, perhaps we could improve. But no, it's so. I invite all of you to address in your domain where you have analytical on digital simulation. Try to improve them with this kind of technique.
Okay, great. Thank you so much. And I agree on the quantum. So based on your explanation, so I see that the physics-informed neural network can be, for example, based on the Schrödinger equation to simulate quantum physics. I don't know if I'm getting it right.
Yes,
yeah,
yes.
Me too.
Yes.
I see it like a disruption, combination. Okay, thank you so much.